when you picture global commerce, well, you're probably picturing thousands of these massive vessels, right? Just gliding across oceans, carrying, what is it, 90% of the world's goods. It's the absolute backbone of, our global economy. But here's the catch, the really critical point. This essential industry is also, well, a major contributor to greenhouse gas emissions. So what if we could give every single one of these ships a constantly updating digital doppelganger, a digital twin specifically designed to make that vessel and maybe the whole fleet truly green? That's our deep dive today. We're exploring the really transformative potential of digital twin technology in shipping. And we're looking at it specifically through the lens of this groundbreaking initiative called the Twin Ship Horizon Europe Project. We've drawn our insights for this deep dive directly from a key research paper that details the Twin Ship Project's, well, its innovative approach. So our mission today is basically to unpack how this cutting-edge tech actually works, the significant hurdles it's designed to overcome, and maybe most importantly, the incredibly ambitious environmental targets it aims to help the maritime sector achieve. Okay, let's start by setting the scene then. The shipping industry. It's this massive global network, totally indispensable to our lives, but like we said, it's also a major source of greenhouse gases. What's the scale of this problem and maybe the potential for change here?
Yeah, what's truly fascinating is the sheer magnitude of the challenge, but also equally the immense opportunity. I mean, look at the global maritime digitalization market. It was valued at what, $157.4 billion back in 2021, and it's projected to just skyrocket to $423.4 billion by 2031.
Wow, that's huge growth.
Exactly. So this isn't just about environmental impact, though that's critical. It's a profound economic and technological shift that's happening. And at its heart, a digital twin in this context is essentially a virtual replica of a physical vessel. Its core purpose is to effectively utilize what the research calls extreme data.
Extreme data. Okay, that sounds pretty intense. What exactly does that mean for a ship's digital twin?
Think of it like trying to drink from a fire hose, basically. You have a massive amount of data. It's high-dimensional, large-scale, often messy, sometimes incomplete, and it's constantly changing. This comes from all sorts of places. Real-time sensors on the vessel, IoT stuff, original ship design specs, construction details, operational logs, maintenance records, even retrofitting information. And this technology is absolutely crucial because it enables what the research calls the green and digital evolutions in shipping. The ultimate goal, a smooth transition to net zero emission ship operations by 2050.
Okay, so if this technology holds such immense promise, both for the environment and clearly the economy, why isn't every ship already a digital twin? What are the big roadblocks? What slowed down adoption across the industry?
Yeah, that's where it gets really complex. One major hurdle is actually in the limitations of the traditional models they use, the hydrodynamic models, the ones used in ship design. While they're valuable for that initial phase, they just fall short when it comes to predicting how a vessel behaves holistically during real-world operations.
Oh, so what's missing?
Well, they can't easily incorporate live ship performance data from when the ship is actually out there working. And the data quality itself is a huge issue. Measurements can get corrupted by harsh weather conditions at sea, making it incredibly difficult to get an accurate picture of what's really going on.
Right. And beyond just the sheer amount of data, what about the quality? I mean, shipping isn't exactly a controlled lab environment, is it?
Exactly right. The complexity and the inherent quality issues of the data are enormous problems. You've got onboard data handling complexities like sensors failing or data acquisition systems going down, or even unexpected degradation of ship systems. And because this data is collected in these really harsh maritime conditions, it's often full of sensor noise. This leads to what the research terms extreme data and anomalies that are just hard to interpret reliably.
Okay, and I can imagine even if you could get all that data reliably, companies might be hesitant to share sensitive stuff like ship routes or business processes. Is that a big blocker?
Oh, absolutely. The commercially sensitive nature of vessel data is a huge restriction. It significantly limits sharing among stakeholders, which, directly hinders digital twin development. And even if you somehow crack that nut, then you run straight into another challenge. A lot of ship owners simply lack the in-house capability. They don't have the time, the budget, or the specialized competence needed to analyze these huge data sets or implement complex machine learning and AI applications across their whole fleet.
So a skills gap, too.
Definitely. There's what the paper calls a notable siloed nature of expertise. You've got data scientists over here, maritime experts over there, business managers somewhere else, and they're not always connecting effectively. It creates a significant workforce skills gap.
And are the tools even there? Are there widely available tools to start this process?
Not really, not in an open way. There's a clear absence of open source digital tools, common data standards, interoperability frameworks, and even the necessary computer infrastructure to support all the diverse shipping stakeholders. So yeah, all these factors combined have created pretty significant technical and commercial barriers. This has led to, frankly, limited success stories so far, and a fair bit of skepticism in the industry about the actual business value of digital twins, which naturally raises the big question: how do we actually overcome these really deeply ingrained hurdles? And this is where the Twinship Horizon Europe project comes in. It proposes a truly multifaceted methodology to tackle them head-on.
Okay, so Twinship is the proposed solution. What's at the core of their approach? How are they trying to make this digital transformation actually happen?
Right. At the heart of it is something called the Vessel AI digital platform. Now, this isn't just a concept, it's an actual open source platform. It was developed through a collaborative European project before this one. And it's engineered specifically for large-scale data processing and advanced machine learning, AI applications, that sort of thing. What's really crucial here are its secure data sharing capabilities. It features what's called a federated data space with specific encryption designed for maritime data. This directly tackles those commercial sensitivity issues we were just talking about.
Okay, that sounds like a huge step forward right there, addressing the data sharing fear. But how does it make sure everyone's speaking the same digital language, with all the different systems on different ships?
That's a great question. It ensures something called semantic interoperability. It does this using common vocabularies and ontologies. Think of it like having super smart digital librarians. They don't just store the data. They understand how all the different pieces relate to each other. So engine temperature gets linked to fuel consumption and propeller RPM, for instance.
Ah, so it builds context automatically.
Exactly. It creates this rich, interconnected picture of the ship's entire ecosystem. This allows for a uniform understanding of data across diverse vessels, different systems, even across an entire fleet. And the fact that it's open source is key too. It means it can support future collaborative projects, really fostering open innovation in the sector. Now, integrated into this platform is the Vessel Data Cloud Space, or VDCS. You could think of the VDCS as the ship's dedicated digital brain, basically. It's designed specifically to structure and maintain those intricate relationships among all the diverse data sets: ship speed, engine data, propeller info, weather conditions, you name it. It uses open source, scalable, FAIR data pipelines. FAIR stands for Findability, Accessibility, Interoperability, and Reusability to ensure data management is trusted and, importantly, sovereign.
Okay, so we have the platform, the data space. This handles the collection and organization. What does this all mean for the actual twin itself? How do they build these sophisticated digital replicas that represent an entire ship, not just, say, the engine?
Well, it's a truly holistic approach. They integrate data from pretty much all stages of a ship's life cycle into the digital twin model. From the very first blueprint right through to its final journey, every data point can contribute.
All stages. Like what, specifically?
Yeah, so for example, the design phase. This brings in hull drawings, hydrodynamic calculations, engine and propulsion system configurations, data from model tests, sea trial data, all the foundational stuff. Then there's the construction phase. This includes costs related to actually building the vessel and, crucially, integrating any green fuels and technologies right from the start. During the operation phase, you have the real-time ship performance data continuously collected and feeding straight into that VDCS we talked about. The maintenance phase adds data on costs and the condition of ship systems, also feeding back into the VDCS, building that historical picture. The retrofitting phase is important too. It includes cost data for potentially upgrading the ship with green fuel or technology options later in its life, and even the scrapping phase contributes data mainly from vessel recycling. Though the research does note this data might be more like average approximations because it's hard to know the exact material composition sometimes. And the VDCS itself, it's structured cleverly in layers. It uses high-level knowledge graphs and these ontologies we mentioned, combined with low-level machine learning and AI algorithms to organize this absolutely vast amount of data. This robust structure allows them to integrate various green fuels and technologies directly into the digital twin models for simulation. This could be for figuring out potential retrofit applications on existing ships or for designing completely new builds. We're talking everything from batteries and cold ironing that's plugging into shore power to LNG, methanol, green ammonia engines, even things like wave and wind energy harvesting devices.
Wow, even harvesting wave energy.
Yeah, and propeller mods, hull coatings, air lubrication systems, gate rudder technologies, you name it. What's really innovative is that even technologies that are still only at the model stage or in lab conditions can be incorporated to quantify their potential performance.
That's an incredible amount of data covering the entire life of a ship. But okay, building the twin is one thing. How do they make sure it's actually accurate, that it's trustworthy and, genuinely useful? And critically, how does it help ship owners make those really big, real-world, multi-million-dollar decisions?
Right, that's absolutely key. And that's where the rigorous model evaluation methodology comes in. It's multi-layered. There are internal evaluations that quantify the accuracy of things like data clustering and regression models. They specifically evaluate the trustworthiness and, importantly, the explainability of the machine learning and AI models. You need to know why the AI is saying something.
Okay, so you can trust the black box a bit more.
Exactly. Then there's an external evaluation that compares the predicted ship performance from the twin against the actual performance data coming back from the real ship. They even use hardware in the loop, or HIL, testing. This is for testing green fuels and technologies that might only exist in simulated or lab conditions currently. And it's worth noting, the outcomes of all these evaluations are actually designed to contribute to industry standards. The project is engaging directly with the ISOD committee that deals with the Internet of Things and digital twin standards. Now, managing the quality of all this extreme data, that's another huge piece. There's a really sophisticated data quality governance strategy, or DQGS. Think of it like a highly advanced digital doctor, constantly checking the ship's vital signs. The extreme data from the VDCS first passes through what they call Data Anomaly Filter 1. Then primary MLAI algorithms cluster the data into localized operational modes like specific engine modes or trim modes. Secondary MLAI, using a technique called singular value decomposition, SVD, creates mean surfaces for these clusters. This forms Data Anomaly Detection Filter, DADF2, which identifies secondary, maybe more subtle anomalies.
So it's filtering, then filtering again based on the clusters.
Precisely. And it gets smarter. There's a data anomaly knowledge database that classifies these anomalies, figuring out if it's a genuine system, abnormal event, or just a sensor or data acquisition fault. Then, a data anomaly recovery strategy, DRRF, uses that SVD structure to actually recover or reconstruct the data where anomalies were detected and classified, feeding high-quality, clean data back into the system. This continuously improves the digital twin model's accuracy over time. It's not just filtering bad data, it's a self-correcting system that learns and purifies the information stream.
So the digital twin isn't just accurate today, but it stays trustworthy because it's constantly self-correcting itself based on real-world feedback. That sounds like the real genius here.
That's exactly it. It ensures the digital twin always gets the purest, most reliable information possible, no matter if you hit stormy seas or have system glitches. This entire, quite complex process is designed specifically to ensure the explainability and trustworthiness of AI for digital twin applications in shipping. It's not just about accuracy, but confidence in the outputs. And all of this sophisticated data handling and modeling feeds into the Decision Support System, the DSS, which includes a powerful simulation environment. Its ultimate purpose is to simulate these highly accurate digital twin models to improve both the day-to-day operational actions and those really big, long-term strategic decisions. There are kind of two main levels to this DSS. First, there's an onboard DT-enabled DSS. This is used directly on the pilot vessels themselves for near-future scenarios. It integrates things like voyage optimization. The expected outcome from this, just from the voyage optimization on the pilot vessels, is a significant 20–30% GHG reduction per voyage, simply by maximizing energy efficiency for that specific trip.
Wow, okay, 20–30% just per voyage is huge. And you mentioned voyage optimization. What's the difference between, say, just avoiding bad weather and truly optimizing a route for energy? Is there more to it?
Yeah, that's a great distinction they make. It differentiates between what's often called passive weather routing, basically, trying to navigate in calm weather, mainly for fuel savings, and active weather routing. Active weather routing actually involves potentially navigating in moderate or even rough weather, but doing it strategically to harvest renewable wind and wave energy, using those conditions to your advantage. It's about turning potential challenges into opportunities for efficiency.
Interesting. Turning the weather from an enemy into an ally, potentially.
Kind of, yeah. Then there's the second level, the onshore DT-enabled DSS. This is used more for the mid- and long-term decisions, the ones related to the entire ship life cycle. Key features here include life cycle cost analysis, or LCCA, and environmental impact assessment, or EIA. This is the module that helps with those critical decisions about ship design, about retrofitting existing vessels with new green tech, or planning completely new builds. It does this by modeling different green fuels and technologies within the digital twin, simulating their performance and providing crucial return on investment, or ROI, predictions. This is vital for figuring out how to meet those IMO greenhouse gas reduction goals cost-effectively. It can even help technology providers themselves develop more focused, effective solutions by showing what works best in realistic scenarios.
So the onshore system looks at the bigger picture, the long game.
Exactly. The digital twin models are simulated at different levels. You can model existing vessels with their current technology, or simulate them upgraded with future tech, or model entirely new builds, all through the lens of route optimization, life cycle costs, and environmental impact. The overall outcomes you get from these DSS simulations are things like improved ship energy efficiency and reduced emissions forecasts, details cost-benefit analyses for various green fuels and technologies, and really valuable insights into possible future environmental regulations and how to strategize for them.
So, okay, with all this incredible technology, this meticulous data management, the simulation power, what are the big headline goals here? What impact is Twinship actually hoping to have on the future of global shipping?
Well, the goals are nothing short of transformative, really. For the pilot vessel demonstration phase, like I mentioned, they're expecting that 20–30% emission reduction just from the voyage optimization piece. But looking broader, the whole project is designed to support achieving really significant greenhouse gas reduction targets for the entire world merchant fleet. We're talking around 118,928 vessels globally.
Wow. Okay, what kind of targets are we looking at for the whole fleet?
The targets compared to 2008 levels are ambitious. A 30–40% reduction by 2030, then ramping up to 80–90% reduction by 2040, and ultimately achieving net zero emissions by 2045.
Net zero by 2045 for the entire global fleet. That's
Yeah.
incredibly ambitious.
It is. And these targets are planned to be achieved by carefully considering both existing and emerging green fuels, modern technologies both for retrofitting older ships and for new builds, and factoring in how mature those technologies are likely to become over the next 20 to 25 years. The project also specifically highlights the significant contribution they expect from renewable energy solutions, like the wind and wave harvesting we touched on. And they even mention the potential deployment of an unmanned net zero emission vessel concept as a kind of futuristic vision. So, in essence, the proposed digital twin and DSS framework is designed to fundamentally support the shipping industry in hitting these absolutely critical environmental milestones. It's about fostering both sustainability and innovation in maritime transport on a truly global scale.
What an absolutely eye-opening deep dive we've taken through the Twinship project. It's fascinating. We've seen how these digital twins are actually being built. I mean, from that intricate process of integrating data across a vessel's entire life cycle, design, construction, operation, maintenance, even scrapping. It's incredible. And then how they use these twins in sophisticated simulation environments to drive both, the day-to-day operational efficiency and the really big strategic long-term planning needed for decarbonization. The key takeaways seem pretty clear. Digital twins hold this enormous potential to fundamentally transform global shipping, but it's definitely not a simple switch you just flip. It involves tackling these really complex data integrity challenges, addressing that significant skills gap across the industry, and leading truly innovative, open source, and holistic approaches like the one Twinship is pioneering if we're going to meet these incredibly ambitious net zero emission targets. It really makes you think. As we move towards this truly digitized maritime future, where our global supply chains become even more reliant on these intricate digital ecosystems, what new challenges, perhaps beyond the purely technological, might we need to start preparing for? Something for us all to consider.